Chapter 2, Operator Algebra and the Mathematical Architecture of Numeric Differentiation. The process by which specific numbers emerge from the primordial supersymmetric zero state is not random or arbitrary. It is governed by a set of mathematical rules, specifically by a well-defined operator algebra that acts upon the infinite-dimensional Hilbert space introduced in the previous chapter. This algebra is not just a formal tool, but the essential mechanism through which undifferentiated potential collapses into actual numeric outcomes. At the heart of this framework is the number operator, usually denoted as n hat. The action of n hat is simple but profound. When applied to a basis state, which we call ket n, it returns the number n multiplied by the same ket n. In spoken terms, if you apply n hat to ket 0, you get 0 times ket 0. If you apply it to ket 5, you get 5 times ket 5. In general, for any non-negative integer n hat acting on ket n yields n times ket n. This operator is more than a tool of convenience. It is the generator of all numeric structure within the Hilbert space. Each basis state is defined by its unique eigenvalue under the number operator, meaning that different numbers correspond to different directions or axes within the possibility space. This property allows us to distinguish one number from another in a precise, algebraic way. But what happens when we apply the number operator to the supersymmetric zero state? Recall that this state, which we call ket z, is a superposition of all number states, each weighted by its coefficient c sub n. The action of n hat on ket z is as follows. For each term in the sum, n hat pulls out the value n from ket n, resulting in c sub n times ket n. When you add all these up, you obtain the following sum. For all n starting from 0 and going to infinity, sum the quantity c sub n times ket n. This result is critical because it demonstrates that the supersymmetric zero state is not an eigenstate of the number operator. In spoken language, this means that applying n hat to ket z does not simply scale ket z by a single value. Instead, it produces a new superposition in which each term is weighted by n times c sub n. The zero state is therefore a true superposition of all numeric possibilities. It does not have a definite number, but rather encodes the potential for every number to emerge through the process of collapse. To understand this further, we calculate the expectation value of the number operator in the zero state. This quantity tells us the average number you would expect to obtain if you were to sample from the zero state repeatedly. The expectation value is given by the inner product of ket z with the number operator acting on ket z. In equation form, this is the sum over all n of the squared magnitude of c sub n multiplied by n. In other words, for each possible number n, take the probability amplitude squared, multiply by n, and sum over all n. Let us consider the special case where all the coefficients have equal amplitude, which is the perfectly symmetric scenario. In this case, for a truncated sum up to n, each coefficient c sub n has an absolute value of 1 divided by the square root of n plus 1. The expectation value then becomes 1 divided by n plus 1 times the sum of all n from 0 to n. This sum, as we know from arithmetic, is n times n plus 1 divided by 2. Therefore, the expectation value simplifies to n divided by 2. This means that, in a perfectly symmetric zero state containing numbers from 0 up to n, the expected value of a measurement is simply the arithmetic mean of all possible numbers, that is, halfway between the minimum and maximum. As the upper bound n approaches infinity, the expectation value also increases without bound. This reflects the fact that the supersymmetric zero state contains arbitrarily large numbers in its superposition, with no finite limit. However, the expectation value alone does not capture the full richness of the zero state. To understand the diversity of possible outcomes, we calculate the variance of the number operator in the zero state. The variance measures the spread or dispersion of possible values. It is defined as the expectation of the square of n hat minus the square of the expectation of n hat. First, we calculate the expectation value of the square of the number operator. This is given by the sum over all n of the squared magnitude of c sub n times n squared. In the symmetric finite case, this becomes 1 divided by n plus 1 times the sum of n squared from 0 to n. This sum evaluates to n times n plus 1 times 2n plus 1 divided by 6. Therefore, the expectation value of the square is n times 2n plus 1 divided by 6. The variance is then computed as this value minus the square of the mean. The mean, as we have shown, is n divided by 2, so its square is n squared divided by 4. Subtracting these yields the expression n times 2n plus 1 divided by 6 minus n squared divided by 4. This simplifies through straightforward algebra to n times n minus 1 times n plus 1 divided by 12. For large values of n, the variance grows proportionally to n cubed. In spoken terms, as the range of possible numbers grows, the uncertainty or spread of outcomes in the zero state grows even more rapidly. This shows that the supersymmetric zero state is not just balanced, but also maximally generative. It contains the greatest possible potential for diverse numeric outcomes through the act of collapse. Now we turn to the crucial question: how do specific numbers emerge from this sea of possibility? The answer lies in the definition of the collapse operator. For any given number n, we define the collapse operator, pronounced c hat sub n, as the projection onto the basis state ket n. Formally, c hat sub n equals ket n times bra n. In more accessible terms, this operator, when acting on any state, extracts only the component along ket n and zeroes out all others. Applying the collapse operator to the zero state yields the following: c hat sub n acting on ket z equals c sub n times ket n. The probability of obtaining the specific number n upon collapse is the squared magnitude of c sub n. In this way, the process of collapse projects the entire symmetric superposition down to a single numeric outcome, with probabilities determined by the structure of the zero state. The overall mechanism of differentiation is now clear. The supersymmetric zero state is the starting point. Collapse operators act upon it to produce definite numbers, each with probability equal to the squared amplitude of its corresponding coefficient. The symmetry of the initial state ensures that, in the absence of bias, all numbers are equally likely, but the framework allows for more general distributions if desired. To extend the picture further, we introduce the concept of continuous collapse operators. Instead of projecting onto a single basis state, these operators interpolate between the fully supersymmetric state and the fully differentiated state. We define a family of operators parameterized by a variable lambda, which ranges from 0 to 1. When lambda is 0, the operator returns the original zero state. When lambda is 1, the operator fully collapses the state onto a definite numeric outcome, according to some probability distribution p sub n. The continuous collapse operator, pronounced c hat of lambda, acts on ket z as follows. Take the square root of 1 minus lambda, multiply by ket z, then add the square root of lambda times the sum over n of p sub n times ket n. This construction allows us to study the gradual process by which perfect symmetry is broken and specific numbers emerge. By tuning lambda, we can interpolate between pure potentiality and actual differentiation. This entire operator framework provides a rigorous mathematical model of numeric emergence. It shows, step by step, how the undifferentiated zero state gives rise to the full arithmetic universe, not by arbitrary choice or exogenous fiat, but through the precise, deterministic, and probabilistic action of operator algebra on an infinite-dimensional Hilbert space. This model not only resolves the logical problems of numeric origin, but also provides new tools for understanding emergence, symmetry breaking, and the deep architecture of number itself.